All right, in this video, we're going to take a look at both example 4 and example 5. Now, for example 4, it's really easy. I just wanted to go ahead and have you use the 3D plotter again to try to graph some crazy looking vector function that we can get here. All right, I'm going to go ahead and go back to the 3D plotter and type this in to get a sense of what this looks like. There's not really anything to write down here. But let's go back here. I'm going to go ahead and adjust the window again, back down to 2 from where we had it in the last video. And then in here, I'm going to start typing in exactly what I have for each of my components. So one thing that you can kind of see here as we're typing this in is that in the x and the y direction, I kind of have sine of t and cosine of t as like this multiplier to the quantity. And then in the other direction, I also have a cosine function. So we should be able to predict something kind of almost immediately about what this graph might look like. First, we wouldn't be surprised if we see any sort of circular shapes. That would be pretty expected. But also, we should expect that the graph should be fairly bounded. That is, we shouldn't expect the graph to kind of stretch really far in the x direction, because sine and cosine can only ever get so large. And similarly for all the other directions. If I hit enter, whoa, I get some sort of really funky graph. Okay, now this isn't really that surprising. It's not weird to get something like this. In fact, your calculator would produce something like this back in an algebra class if your calculator wasn't plotting enough points. Calculators create their graphs by essentially just plotting a bunch of points and playing connect the dots. If you don't plot a lot of points, you get these really kind of jagged connections between dots. So to help the calculator know that you want it to plot more dots and hopefully sketch a smoother picture, you can always go here to this number of steps. So like here, I'm going to increase this from 100 to 200. And if I do this, okay, like I'm getting like a little bit better, maybe. Let's go ahead here and adjust my window as well. I'm actually just going to have this go from, say, negative pi to positive pi. Okay. So I don't have as much there. I was going, from a much larger range before. But here, negative pi to pi, it's like a 2 pi length interval. And I can start to see the graph a little more clearly now. Okay, can you kind of see there's like the spiral action actually going on here? It's still a little jagged, so if I wanted, what would happen if I increased to 300? Okay, can you see it just got a little smoother? If I went to 400, it's even still more smooth. But I can kind of see the shape that I have here. You can always use a scroll wheel to kind of zoom out if you need to see a little bit more on the picture, but here's the graph, right? It's like a slinky. That's kind of cool, right? This is a very complicated equation that creates this graph. Again, a lot of this sort of behavior was somewhat predicted by just some of the stuff that we actually saw within the formulas themselves. All right, let's take a look here, though, at something like exam 5, because a lot of the questions that I get typically from students is like, Kyle, if you were to ask me on exam 2 a question related to this first section, what would that question look like, right? And like typically, it could look either like a question like example 5, where I would say, hey, here's a graph. Could you tell me what function that you have? Or you could imagine the reverse. Here's a function. Can you tell me which of the graphs matches to it, right? Because that's about really all we're dealing with here. Okay, so let's take a look at a style of question like this, right? Can we match each of the different graphs below to one of the following vector functions? Don't use that 3D plotter. We want to try to reason through this. Okay, let's take a look here at the first graph, graph A. What do you notice about it? Well, there's a couple things we might notice. First off, can you kind of tell that there's a spiraling behavior going on that graph, right? Like it's looping around. That's interesting, because that means if you were to try to squish that back down, you just might have some sort of a circle. So immediately I'm going to be interested in saying, okay, I should have a circle moving in 2 directions, but then free movement in the other direction. So when I'm dealing here with graph A, there's a couple options here I think I can immediately eliminate. I don't think that graph 2 would make sense, because notice, while I might get some circles, I don't have any free motion within another direction. And that's kind of what I need. I need to be able to kind of go up as far as I want. Similarly, then, number 4 doesn't really make sense here. The last thing, though, I could notice is that this free motion needs to happen in the z direction, right? I need to spiral in the x and the y direction, but I need to kind of increase upwards unbounded in the z direction. Which of these then remaining graphs maybe fits with graph A? Well, I would think graph number 1. Notice I have that circular shape in the xy direction, but I have an unbounded motion in the z direction. I think that fits perfectly here. All right, let's take a look now at graph B. What can I say about graph B? Well, notice immediately graph B is not unbounded. It's kind of existing in a very restricted space, right? The entire graph is apparently fitting within this box. It doesn't look like it's ending or has the potential to kind of keep going. So I think that automatically allows me to get rid of option, not option number 4, option number 3, because this had an unbounded value for y. Now for all of the other values that I have, or the other functions that I have here, that is functions number 2 and 4, maybe those do work for graph B. If I wasn't sure which of those might work, one thing that I could do is I could always attempt to plot a point on these functions and see which one maybe actually matches up with the graph that I have. So let's suppose, for example, that I was to go ahead and plug in the value of t is equal to 0. Note that my second function would then create a vector of, if t was a 0, I would create a vector of 1, 0, 1. And my other vector would be just 1, 1, 1. So what I could do is try to see, do these points occur within this graph? Let's try to check. If I went 1 down the x-axis, I would be right here. If I went 1 down the y-axis, I would then be about here. And if I went 1 up the y or the z-axis, I would be about here. So, does this point appear like it's actually on the curve? It doesn't. So I'm a little tempted then to say, assuming that I drew things correctly, that 1, 1, 1 is not on the curve. Let's double check then that 1, 0, 1 would be on the curve. If I went 1 out in this direction, I didn't go anywhere in the y direction, and I went up 1 unit, that would put me about here. And notice that is a point on the graph. So I would guess that my second graph actually goes with graph B. And I just kind of did that by process of elimination rather than actually sketching out the whole graph. Okay. Hopefully this gives you a sense that I should be able again now to go both ways. If I had a picture, I might be able to pick out the graph from, or pick out the vector function formula from a lineup. And if I had the vector function formula, like in previous examples, I might be able to make some predictions about what that graph looks like. In the next section, we're going to be getting into a little bit more of the calculus behind these vector valued functions. If you're practicing the concepts from this section, you happen to have any questions, feel free to let me know.